Hello, my name is Aisling. I work at Taceo, and we work on co-SNARKs, collaborative SNARKs, and private shared state. So I'll give you a bit of an introduction to what those things are. Um, so yeah, as I said, we work on collaborative SNARKs. We had a quick chat already, so I know who of you know about this already. But basically, what collaborative SNARKs are is like a combination of multi-party computation and zero knowledge proofs. So you generate a zero knowledge proof in a multi-party computation environment. We'll get to what that means in a minute. But why do we actually even care about this? Because what we really want, or what I really want, and what I hope to convince you that you really want, is to create this world where a private shared state exists and is a thing. And so then you might ask, okay, what is private shared state? And so, I mean, one thing for me that was interesting when I started kind of looking into this stuff was the fact that there are different state models. And like, I think with Ethereum, it's very easy to just kind of accept reality. Okay, Ethereum came around and like there's this, public state transition machine that, yeah, you have this and everybody uses this and whatever. And so you kind of don't really question, is there another way, or are there other ways to use this data or this state that is created on Ethereum? But yeah, it gave us this public shared state. And this was really nice because like everybody can look at Ethereum, everybody can verify whatever transactions, and this is great. But then these scalability issues, like it's slow. This led to some people to develop things like ZK rollups, whatever, like doing some sort of state transitions that can be done much faster, and you publish uh, the state update to the original L1. And so because we had all this kind of ZK technology stuff for scalability, actually it turned out that, zero knowledge in the first place was kind of a privacy tool. This was kind of thrown away because people wanted to use it for the scalability. But since there were kind of big advancements in the scalability, it was like, hang on, if we just add the privacy back in, we get like a whole new feature kind of for free. And then there are these ZK-centric chains that came about, like Aztec, Aleo, Mide, and Midnight. And they are kind of built on the premise that, we have this zero knowledge rollups, let's say L1s, L2s, whatever, they're different, but like we have this zero knowledge tech, we can do some blockchains around this now. And so this sort of introduced kind of what I find a bit interestingly, this new type of state, which is just a private state. Either it's like sitting locally on your device, client side, or you have some sort of encrypted state or like a proof on chain or something like this. And so now you have this kind of two state models. Like you have this public shared state of Ethereum that everybody can read and everybody can check and verify it's public and
Low
everybody can see.
battery.
And
Please
then you also have
charge.
these kind of like local isolated private states. And this is, yeah. And so this public state that Ethereum gave us is super nice because you have composability on this. Like you have, like everybody can check it. And because it's there, publicly available, publicly visible to everybody, anything you build on top of this, any application that you build that uses this state can kind of, can use it any way it wants and can kind of build stuff on top of the stuff that it builds. And you have this composability. And you see this in DeFi. I do a DeFi smart contract for a lending protocol or something like this. I can do another like smart contract on top of that. And you have all these building blocks that you can piece together. And the reason you have this composability is because everything is public and everybody could see whatever. The private state is nice in the sense that, okay, now we have some privacy, we have some cool ZK apps. Like, I hope like I don't have to convince you that privacy is a good thing. Like privacy for Ethereum is great in the sense that everything is public and you have this verifiability. This is needed for things like, the reason that all this blockchain stuff came about is because we wanted to burn the banks and whatever. We don't trust the institutions. But this comes then at the cost of like all like individual users having to suffer and lose privacy. And I think this kind of sucks. So it's like, yeah, sure, we need public verifiability for some stuff, maybe for the institutions, but for individuals, maybe this is not good. Nobody wants their bank account details, like every transaction, posted publicly in the town square. So yeah, privacy is good. It gives us these ZK apps, which are nice. But the limitation with its private state now is that like it's sitting locally on my device or it's sitting encrypted on a chain and it's all isolated. And like, so you lose this sort of nice composability that came about with Ethereum, and you lose this kind of chance to, like remove this barrier to entry of computation that Ethereum gave you and this kind of stuff. And so the question is a bit like, is there a way to bridge these types of things? Is there a way to like have your nice private state that you want, but also have the composability that you had with the public shared state of Ethereum? And so this is what we call, and others in the industry call now, this private shared state. Is there a way to have a private state that is somehow composable? Like, while you maintain privacy, can I sort of take some private data from here, some private data from here, do some computation or state transitions over the two separate private states? This is what we call private shared state. In reality, this means that we need to do stuff, something like computing on encrypted data, because you have private data, encrypted data here, encrypted data here. You want to do some computation across them, you're doing computing on encrypted data. There's kind of no other way around it. And at the moment, like you hear a lot about FHE, so homomorphic encryption. You hear a lot about TEEs. This is not really encrypted data, but yeah, you have this sort of private computation. There's also, yeah, ZK, but then it's limited in the actual functions that you can evaluate on this private state. You can prove relations and things like this, but you cannot do any sort of function evaluation. So we need, like, for composability in this sort of ZK world that we're all kind of living in, for sure you need verifiability, and you need to compute on private inputs. Computing on the private inputs, this is like the classic case of MPC, so multi-party computation. And having verifiability on data without revealing stuff, this is the classic case of ZK. And so you have this kind of scenario where you're like, okay, I want to compute on different data across different places, private data. I also want to verify this and be able to push stuff on chain. So you have this like, okay, we need MPC, we need ZK. Is this possible? Like, is it possible to do ZK proofs in MPC? Is it possible to combine these? Are the overheads massive? And yeah, collaborative SNARKs. So you end up, yeah, doing ZK and MPC and having these collaborative SNARKs. We go into this in a minute. And so these came about in 2021. There was a paper from Dan Bonnet. And I think, and basically, like, the premise is that you want to do a zero knowledge proof in an MPC environment. And so like here, normally, like, this is the single prover, like normal plain, like zero knowledge proof world as you know it. You have a witness, so some statement about some data. My name is Ashling, I'm over 18, that testifies to some fact, which is given as input to just an algorithm, a prover, which produces a proof on this witness, which can be verified by a verifier. Classic ZK. What they wanted to do with the collaborative SNARKs is to say, like, okay, I think at the time there was a lot of like these prover networks coming about. People like outsourcing proofs was kind of becoming a thing. People couldn't do proofs on their phones anymore. The proof systems were getting a bit too heavy and too clunky, and like the needs were getting bigger, and so people needed to outsource. And the question then becomes, okay, if I'm concerned with privacy and I want to outsource proof to a prover market or something like this, is there a way that I can do it with, like, without revealing the witness to everybody, because this is some sort of secret data? And so, yeah, they do this in MPC. And so the thing you do with MPC is you take your secret data, you secret share it into different pieces, and then you send those like encrypted secret shares to different provers. So now you're in a case where you have 3 different provers, which generates a proof that can be verified by a prover. A verifier. And so, yeah, the approach was to run ZK provers in an MPC environment. And in terms of crypto, like cryptographic developments, this is not a huge development. But I think one of the nice things that they did with this paper was that they kind of showed that, like ZK, if you're doing a zero knowledge proof instead of, a plain computation, there is some overhead. And the same with MPC, like there is some overhead in terms of computation if you're computing on private data compared to plain data. And so the intuition is that, like, okay, if you do ZK inside of MPC, these kind of overheads multiply and get huge. And that's not so desirable. And what they showed is actually that's not the case. Like, usually if you do some ZK, you have some overhead. If you do this in MPC, there's no extra overhead. So you get it, like, you get the MPC part kind of for free if you do things.
Low battery. Please charge.
And so this is what we do. We sort of implement this sort of MPC stuff where you can write, actually, I can show you, but like if you want to write proofs in Circum or in Noir, so far, these are the two kind of environments that we're doing it for. You can do it in an MPC environment. And so, yeah, we were doing like MPC-ifying the proof systems basically that exist. I won't go into this so much. It's just we can read about it later, but it's a bit more of the details of like why there isn't much overhead. And this is mostly for elliptic curve-based provers. So like this is not any of the SNARK stuff. And so, yeah, the simplest language framework for generating proofs is Circum. So this is where we started. And so we added functions to Circum to get what we're calling co-Circum, collaborative Circum, where you can generate Circum ZK proofs in an MPC environment. We adapted the provers
Low
to
battery.
get
Please
co-Circum.
charge.
And we're also doing it for Noir from the Aztec team. So adding the functions to get co-Noir and adapting their provers as well. And so how does this look in practice? Is a kind of a crazy picture, but I will try to talk you through it pretty quickly. And so it's just a bit like I explained. Like, so you have, let's say, Alice and Bob. Alice and Bob have like their private data, and they want to compute some function over the private data. The classic example in MPC is like this millionaires problem. So like, I'm Alice, you're Bob. I come along and say, hey, we're big crypto bros. I earned loads on meme coin trading over the last few weeks. You say, oh, so did I. And we try to make a proof like who is actually more wealthy, who has more money. I don't want to reveal how much money I have. You don't want to reveal yours. So we engage in some sort of multi-party computation that can like compute the max of our two salaries or our two earnings, and then produces the output like, hey, she's
Low
richer,
battery.
without
Please
revealing
charge.
exactly the amount. And then the zero knowledge part of this is like, okay, I produce a proof that like, hey, one of you is richer, Alice is richer. And then I want to prove that the computation was done correctly. So like, otherwise you would just be trusting the system. And in this case, there's like Alice who has her input, which is her salary. Bob has his input, which is his salary. For Noir or whatever, it just takes his input. It secret shares the private data into encrypted shares. The shares are sent to an MPC network. So you have these three provers that were like in the previous picture. The secret shares go to each of the nodes in the network. Alice does the same. She secret shares her private data. She sends her encrypted shares to the MPC network. The MPC network then each node does its operations on Alice's share 1, Bob's share 1. The second
Low
node works
battery.
on Bob's share
Please
2 and Alice's
charge.
share 2, whatever. They do their computation. At the end, they produce a result and a proof. So they send. They each send a result back to, let's say, a third party called Charlie, or it could just be a smart contract or whatever. And then you get the output, which is the result of the computation. Alice is richer, and you get a proof that testifies to this fact. And this is what we call a collaborative SNARK because it's done in an MPC way. And so like all the developer needs to do is write a normal Noir or Circom program, and then all of this kind of happens in the back. This is the kind of stuff that we're trying to abstract. And so the goal is to actually be able to generate these proofs, do this computation, generate these proofs with as little overhead compared to a single prover. And the reality is, okay, lots of numbers here, but like, let's say for a dark pool or generating a Poseidon hash,
Low
with
battery.
Noir,
Please
I don't know if
charge.
you know so much about Noir, but it's quite a feature-rich ZK language. And so if you want to do it in MPC for pretty much all of the experiments that we did, it's a bit higher. And if you do it in plain ZK, it's a bit lower. And so with Noir, we're at a very, very early stage. And so these are very, very preliminary results. These are literally the first benchmarks that we did last week. And so there's like zero optimization here. We were just kind of trying to push out features over the last while. For Circom, maybe it's a bit more interesting because, hey, you're looking at like generating Poseidon hashes or like, SHA hashes. And you can see that like compared to, let's say, SNARK.js, actually sometimes you're quite a bit faster because the implementations are just a bit more optimized. And so like compared to plain ZK, you can do this stuff in
Low
MPC with all
battery.
this privacy
Please
preserving
charge.
stuff and be faster actually. And so looking ahead, yeah, like we can just chat about it afterwards, but like this is still very new. This is still kind of like very emerging. I think like maybe you see that people are still kind of onboarding to the idea of ZK. And now we're saying, okay, take your ZK, do it in MPC, have all this kind of privacy preserving stuff. But like we're finding already that it does serve a purpose. Like, and the two kind of main purposes that we see are this private proof delegation. So, kind of as I said before, hey, I have some private data. I don't have capacity on my mobile phone or in my browser to generate the proof because I'm doing some fancy circuits and like, you know, my browser's timing out or my phone doesn't have capacity or I don't want to download like a huge app like with big binaries or whatever. And so I'm happy to interact with like a front end or whatever from my browser or from my phone, but I want the proof to be outsourced. But I want to
Low
maintain
battery. Please
privacy. So I
charge.
want the witness data to not be seen by the prover. There you can use this MPC scenario. So yeah, private proof delegation is one that we see. And also then this private shared state. I have private states in different places and I want to do some computation across them. These are the two main things. And so, yeah, then there's a question like, okay, sure, I can write my program, but then like, where do I actually generate these proofs? And this is what we're doing next, basically. So we had like one demo at DevCon with Cursive team. I don't know if you know those, where they were using an AlphaNet that we built between us, Cursive, and PSE to generate co-snarks. But yeah, if you're interested to experiment, let us know. Yeah, that's basically it. Like just saying, I think for me, private shared state is kind of the use case of
Low
blockchain. Like,
battery.
because I think
Please
people
charge.
often say like, blockchain, why not just use a distributed database? Why not just use like whatever sort of machines? And for me, this is like the one thing that Web3 can do that Web2 can't, because Web2 is inherently centralized. And like no matter what they do with private data, they will see it like in a centralized setting. And so here you have this decentralized setting, you have this privacy, you have composability. It's like all the things that Web3 is built for. And so, yeah, this for me is like the end goal for blockchains. And that's it.